So, good evening to all the attendees and students. So, welcome to week 9 of our Electrical Machines 2 NPTEL program. So, I am Sai Krishna Mulpuri. We will be discussing concepts on AC machines like we are discussing for the past 9 weeks. So, last week we have discussed starting methods of induction machine, and we have seen different kinds of types of starting methods in a induction machine. The same way, we will be discussing another topic this week. So, uh, for any kind of motor or machine, three things are very basic. These three things are very important for any kind of motor. The first one is starting. So, how to start a motor, what kind of methods are involved in starting a machine or motor. And the second one is once the machine is started and once the machine is up and running, how can we control that speed of the machine? So maybe we will have different speed requirements. We want our machines to rotate at x speed or y speed. So how can we achieve that kind of speed control? That's the second important thing. And the third important thing is how to stop that machine. So okay, we have started the machine and we have controlled the speed of the machine, and how can we stop the machine? The technique was the terminology what we use for the stopping technique is braking. So how can we achieve this electrical braking of the machine? So these three things are very basic and also very important for a motor. How to start a machine, how to get a precise and smooth speed control, and how to implement the braking on the machine. So yeah, last week we have discussed starting methods of an induction machines in detail. We have seen for a small motors we can go for DOL, direct online starting, and for a bigger motors these are all for cage kind of motors, not slip ring type. So for these motors we have discussed reactor starting, auto transformer starting, and the best method, which is star delta starting. Now we will move to the second most important thing in the machine, which is called the speed control of the machine. Now about speed control, if we have an induction machine having some kind of torque speed characteristics, we saw the torque speed characteristics of a induction machine 2 weeks before. Now we know how the curve looks like, and now on that curve we want to achieve different torque speed characteristics, that is for different speeds how our curve will look like. So that kind of variation we want to see. So for our understanding purpose and for a clear understanding, I will draw torque speed characteristics again. So we'll see how can we achieve a speed control using our basic torque speed characteristics. So the topic for today is speed control of three-phase induction motor. Yeah, let's say we have a three-phase induction machine which with us, and it is having some certain torque speed characteristics. So we know how a torque speed characteristics will look like. Now from here to here, we know it is a slip and it is torque. If slip is increasing by this side and this side is speed, so this is the starting torque TST, and this is the maximum torque TEM, and this is the slip at which the maximum torque occurs. And okay, and see here the slip is increasing. Here S is equals to 0 and here S is equals to 1, and uh, and the speed is reducing. Let's say at the starting slip is equals to 1 at this section, and so ms will be 0 here, and here here the speed will be increasing in this way. So here the speed will be ns. Okay, now when nr is equals to ns, we know the slip will be 0. But For easy understanding, the topic of speed control, I will redraw this figure as a torque speed characteristics. Now, here we can see the speed is increasing from left to right. Usually we need a torque speed characteristics where my speed will be increasing from left to right. Here it is right to left, it is increasing. So then we will have a easy understanding of how things work, right? So I will just redraw a torque speed curve. So this one is a y-axis is torque and x-axis is speed. So I will start with here. Initially, I will have a starting torque. Here, ns is equals to 0. We know that slip is equals to 1 here. And somehow, okay, I will start from here. I will have a starting torque and have a maximum torque. And I will have a ns speed here. Same curve. If you see the rightmost curve that we know that, so we have just reversed it. Now here we have again, here it is maximum torque, starting torque, slip at which maximum torque occurs, usually around we say 10% slip, usually it occurs. Okay, and here is the ns, it is the synchronous speed at which the rotor rotates. If rotor rotates with synchronous speed, slip will be 0 at this point. Now say we have for this kind of motor, let's say we have some kind of load torque, a constant load torque. So this is the amount of torque that my load is demanding. So my motor should always be able to provide this kind of uh, torque. So yeah, so this is my required load torque. And for example, maybe at this full load, my motor should supply this load torque. So for example, let's say my motor is supplying this particular load torque. So my motor is running at this particular speed. So only when my motor runs at this speed, it can supply this load torque. So for example, let's say this is around, let's say it's 5% at some speed. So this is the speed now, ns1. Okay, this is the speed with which my rotor is currently uh, rotating. Now, from the figure, what we can see is now the topic which we are discussing is a speed control. From the figure, we can see there is a uh, there is a path for the load torque. That is a very constant load torque we have. I can say I have achieved speed control of my motor if I can able to deliver that kind of low torque at different speeds. So then only I can say that I have achieved the speed control. Now, if you want to supply this full load torque at various speeds, so from figure we can see that the speed at that full load is very close to ns. So this one, this speed is ns1, that is the uh, full load speed. Now this difference is very less, it is almost close to ns. Now if I want to achieve a speed control, now my question is, can we able to supply this full load torque at a speed half of my synchronous speed? That's just a question. I want to see whether I can do that or not. Now at a speed ns by 2, can we supply this full load torque at half of ns? So that is what speed control means. Can we do that? So the answer is yes. Yes, we can do that. Now we discussed for a slip ring induction machine in the 2 weeks back. So last week we discussed starting methods, and before that we discussed uh, torque equation derivations for a slip ring machine, and also we have seen how the introduction of external resistances can improve the starting torque, and also how reducing the supply voltage will vary the maximum torque. So that discussions we have done. Now, if we if we did observe those torque speed characteristics there, that is also a kind of speed control. We have achieved very smooth speed control there. I will also discuss those points now. The point we have to observe is for a slip ring induction motor, by changing the rotor resistance also, we can achieve a very good speed control, which is also very smooth. By just introducing the resistance in the rotor circuit, we can get for the same maximum torque, we can get a speed control. We will just see that. So so this is also a speed control which we are talking about. Now we know how a torque speed uh, characteristics for a machine look like. So exactly, this is how it looks like. Let's say I'm just drawing it for understanding purpose. Okay, so this is speed and this is torque and this is the maximum torque. Now, let's say this torque speed characteristics is for a R2 resistance in the external circuit. Now, I am increasing the R2. R2 is now R2 dash, which is R2 plus some R external. At this condition, what will be the how will my torque speed characteristics look like? Now we have seen that our maximum torque won't change because maximum torque formula R2 is independent. My maximum torque is independent of my R2, but my slip, the slip at which the maximum, I will just write it, alpha is equals to R2 by X2. If at all we exclude all the stator impedances and R1, X1, if we neglect all these, we can know that alpha is equals to R2 by X2. Now I have increased the R2 here. If I increase the R2, alpha will increase. Alpha, let's say if initially my alpha is here, now my alpha will be somewhere around here. That's where my maximum torque will occur. Now I will just, right? Now I will further increase the R2 dash, R2 double dash. So again, R2 double dash is increasing means alpha will increase. Now my alpha dash, alpha double dash will occur somewhere here. Now here I will have the maximum torque. Okay, so this is how, sorry, the maximum torque, but the ending speed ns will be same, of course. Here it is ns. Okay. So this one as I increased here, this one here. Now see whenever my slip as we increase the speed, the slip will come down. So at ns speed, my slip will always be equal to 0. So that condition is okay. Here in this condition, slip is equals to 0 and here is equals to 1. So the point which we have to observe is as we keep on increasing the rotor resistance in this way, so this is R2 and this is R2 dash and this curve is for R2 double dash. Now our maximum torque is remain same. My speed at which the maximum torque is increasing, and let's say I have a low torque profile same as the profile which we have in the first diagram, the top diagram. Now we can see by just increasing the resistance in the rotor circuit, I am able to deliver this full load torque at different speeds. Let's say my speed here is ns1, let's say my speed here is ns2, let's say my speed here is ns3. Now we can see we can have 3 different speeds of my rotor which will be able to deliver my load torque. So 3 curves are supplying my load torque And all the three curves which we see, uh, we have achieved a very smooth variation by just varying the rotor resistances. So this kind of variation we have got different speeds, and for each torque speed curve, we are we are able to supply the load torque in all the three cases. So we can achieve a very smooth speed control in case of a slip ring induction motor by just varying the resistances. So can anyone tell what is the problem with this? Because we are getting a very smooth speed control, and in the three cases I am able to supply my load. So what is the problem with the circuit? Can I just increase the resistances and get a smooth speed control? Is it suggestible? Can anyone tell the problem with the circuit? So the main problem is we can't just keep on. Yeah, correct, Govind. So there will be a very huge copper loss incorporated when we just keep on increasing the rotor resistance. So the rotor resistance is increasing means we are increasing the copper loss in the rotor. So we are losing much power to the rotor circuit. So in that way, we are reducing the efficiency of our machine. Although I'm getting a very smooth speed control here, uh, it is not used at all. So this kind of technique, increasing the rotor resistance for increasing like getting a precise speed control, is not at all used at all, because we are reducing the efficiency of my machine. Now we have discussed another method as well, not for speed control, but while we are discussing the torque curves, we have reduced the supply voltage to get different maximum torques. So if I write it, okay. Now this is the speed curve and this is the torque curve. Okay. Uh, let's say we have torque speed this. So this is ns speed. One second. This is ns speed, and this is starting torque, and this is the maximum torque, and this is the slip at which my maximum torque occurs. Now let's say this is at a V1 supply. So okay, now I have reduced the V1 supply. Now we know torque equation, we know 3V1 square by 2 pi ns into some resistance part, everything is there. Now it's proportional to square of the supply voltage. Now whenever I am reducing the supply voltage, its square times my torque will also go down. Now see, as I am reducing my supply voltage, my starting torque will reduce. Also, the maximum torque will also get reduced. So, okay, maybe something like this I will get, and actually not even this close we will get, because if we just reduce v1 to, let's say, v1 by 2, my torque will go down 4 times. It's just square times, right? So like this we will get, and even reduced, so we will get like this. So this is for v1 dash, or this is for v1 double dash. Like this we can get. So even here my alpha won't change, because alpha is equals to r2 by x2. We know that r2 dash by x2 dash, and r2 x2 we are not changing. We are changing the voltage. So just te max, where 3v1 square by 4 pi ns, that that expression will change. Te max will change. This te max dash, te max double dash. Like this it will change. My alpha remains same. For the same torque, uh, like this, low torque is like this, if you can get. Okay, now like this, if you have different torques, and so you can see, even for this kind of torque profile, my motor is able to supply different speeds. You can see from this speed here another speed, the intersection points you can see ns1, ns2, ns3. Here also we are achieving speed control, but you see the disadvantages associated with this kind of method is we will get a very limited range of control. It's not a very wide range of control. It's just all the three speeds which we get are very close to synchronous speed. So we are not getting that wide range of speed control here. And also uh, uh, the second disadvantage is okay. Now I have just varied voltage and I've got three kinds. Now this is my constant torque load. And if I further reduce my voltage, somewhere around I will get like this curve. And okay, now my torque speed characteristic curve is below the low torque means my motor won't rotate at all. So the motor won't pick up the speed and it cannot supply the uh, uh, full load torque. So yeah, we don't get a very wide range speed control in this method, and also we will get a very less options for the varying the voltage. We can only go till some extent of supply voltage. There is a high chance that even if we go a bit lower, my motor won't even start rotating because it's further below the low torque curve. So yeah, that kind of disadvantage we see here. If at all, let's say my low torque is not constant, let's say it's some kind of parabolic in nature, like something like this. Then we can get different speed. From here it is here like this, here it is like this, and yeah, we will get a varied speed range if our low torque is not parabolic maybe. But we can't just depend on our low torque nature to go for such a speed control. So what my main point is, we have some old kind of techniques where earlier methods which I have discussed, where we can achieve speed control. In the first method, where we are varying our rotor resistance, we get a smooth control over speed. At different speeds, we are able to supply the load torque. But the problem with that is we are encouraging the more rotor copper losses. That's not at all advisable. And coming to the supply voltage variation method, even there we are achieving the speed control, but very minimal range of speed control we have achieved. And the scope for even further variation of voltage is not permissible. So even there is another method where if time permits we can discuss towards the end of the lecture or some other time, but there is some other method which is not used at all nowadays, where we will have two machines, one rotor of both induction machines. You have rotor stator. One second. So rotor of one induction machine is connected to stator of another induction machine, such that we will get a different frequencies induced, and based on frequency we will get different speed controls. That's a very uh, old technique, we can say. We can't use that method now because it involves two machines, and it's not very suggestible. Even those are earlier methods we are not at all using now. Now we found all these techniques are either inefficient, like our rotor resistance control method, or we require complicated setups, like one rotor supplying the other, one rotor supplying the other stator. Such kind of complicated setups we require. Now that's why we are not going with all these earlier methods, because even after applying these methods, we see that there is only limited range of speed control, limited speed control we are achieving. That's why when we compare our induction machine speed control with a DC motor speed control, we will get a very smooth speed control in the DC motor. We will have just two methods: armature voltage control and field current control method. So by just controlling the armature voltage of DC machine, we can get a very smooth speed control below rated speeds. And if you want to control the speed above rated speeds, we have to just vary the field current, and we can get the very precise speed control in a DC machine. Now, why can't we do that with an induction machine? So that's the question. So because whenever you want to control the speed with an induction machine, for a given induction machine, our frequency is fixed. right? The frequency of the machine of the stator of this induction machine is nothing but the supply frequency. If the supply frequency is 50 hertz, okay, that's it. My supply frequency is fixed. Based on that, I will get a some synchronous speed, because ns is equals to what, 2f by p, right? It is in rps, rotations per second. Now for a fixed value of f, if it's a 50 hertz machine and also 4 pole machine, okay, that's it. My speed is fixed now. I can't get any other speed, synchronous speed. Now, in DC, in a DC motor, if you can see, using these two methods, armature voltage control and the field current control, we are getting a very smooth control of speed below never rated speeds, because there is no point of frequency in that, in that case. In case of DC machine, there is no point of frequency. Now, with a fixed frequency in induction machine, our NS is fixed. Once the NS is fixed, my rotor speed is also fixed based on the slip at which it is rotating, and R is equals to NS into 1 minus S. I fixed the NS. I fixed, now my rotor speed is also fixed, and it will be very close to synchronous speed. We have seen it in this case. So it will be very close to somewhere around 5% slip. If it is 3% slip, it will be close to synchronous speed. Everything is fixed now. So that's why previously people used to consider our induction machine as a constant speed motor, because there is no point in getting speed control. So let's not use our induction motor for the speed control at all. We will have a very good uh, we will have a very good control. Oh, 1 second. Okay, fine. So we can have a very good control of what say speed using the DC machine. Now, previously, there is also a very one more common question which we have is, in traction motor, in the traction systems, which motor is commonly used? So this is a very popular question which we used to like here in interviews or any machines discussion. So the common answer is DC series motor. So because we need to get a very good speed control. In the starting, we need to have that much torque, and later we have to pick up the speed, and torque should change. So to get such precise control of speed, control, people used to use DC series motor extensively. Nowadays also still DC series motor is still used by the people, but the people were not asking the right question, whether I can use my induction machine to get such a speed control. So it's not that since my supply frequency is fixed, everything is fixed, the induction machine is ruled out of speed control. No. So people were not talking at that point of time when they are using DC series motor extensively for these traction applications, whether this kind of speed control can be achieved with ease using my induction machine. So that question came up then, and then people started to actually look into this problem. So let's say I have an induction machine. Why not I can achieve such kind of speed control with ease using my induction machine? See, that's where the first discussion for a very precise control of induction machine came up. So this is where people started to think, how can we achieve a speed control using a induction machine? So here for a given induction machine, let's say I have ns. This is constant, and hence nr will be constant. So let's say, yeah, ns is 2f by p. If it is constant, nr is constant, that's where somewhere around 5%, 3% slip, nr will be also constant. Now, people thought about introducing power electronics into the machines. Now, power electronics is very developed field in electrical engineering, and even if you see the advancements in the power electronics, everywhere we are using power electronics. If you take any kind of electrical appliance, electronic appliance, we see a power electronics converter there. So, see, under the power electronic branch, we have many devices like rectifiers, AC to DC converters, choppers, DC to DC converters, inverters, DC to AC converters. So everywhere we need these converters because the power levels which we are having from the supplies and also the devices which are compatible. Let's say my phone requires a DC supply and my batteries, those are the DC supplies, and my machines require AC supply, and my supply which was given from the power plant to our households is a single phase AC or three phase AC. Now, when we are having this kind of diverse supplies in it, one require AC, one require DC. Even within DC, I might require less voltage DC. Let's say I'm having a 230 volts single phase supply, but I need 100 volts AC. So how to come to this kind of voltage variations within AC DC? So everything, every power conversions, voltage conversions, level conversions, we use power electronic converters. So power electronics is a very advanced field in electrical engineering. So with this advancement in power electronics, people thought, why not introduce power electronic converters for our problem of achieving a smooth speed control? So then people thought, why not? Because what are the problems people are saying for induction machine speed control? Since my supply frequency is 50 hertz, is fixed supply, my NS and NR are fixed. Now, with the advancement of power electronics, people are thinking, why not can I vary supply frequency? So immediate question is, how can you vary a supply frequency? So supply frequency is fixed for the entire country. It's a 50 hertz. That's what you get a supply frequency. Now, how can you vary? Using the power electronic control. Yes, precisely. You can get a frequency control using the power electronic system. So we can now see how easy it is to control frequency, thereby controlling the speed using power electronics. See, let's see how we can achieve that. So it's very interesting and very once we discuss this, we will also feel how easy it is to control frequency using this power electronic system, and we will further see that if we have a power electronic system like that, we can solve the starting problem also, starting methods problem. So last week we discussed different methods for starting problem. Even those problems are also solved if we use this power electronics converter. Even that also we will discuss it later. But first we will see what kind of power electronic system will achieve such a good frequency control. Okay, let's say here I have my three-phase supply, like it is provided from the grid, right? This I can't change. I mean, this three-phase supply, this is the 50 hertz supply. This I'm not able to change. So the question is, how can we change it? This is a AC supply. Now I will introduce a rectifier here. You can use a diode bridge rectifier or full wave half wave rectifier. You will use a full wave rectifier, of course. Now, using the rectifier, we will convert this AC supply first into a DC supply. Right? This is the DC supply now. Now I will feed this DC supply to a three-phase inverter. What does an inverter do? It will convert DC into AC. Now here again we have AC. Now this works as a three-phase source. Okay. Now this three-phase source which we are seeing here, we should be able to have a different voltage level and different frequency level. Here we are having a three-phase voltage, some line to line voltage we are having, and frequencies some V and F we have, and here we will get voltage and frequency which are variable. That's the whole point. I need to get a variable source here. So for that purpose, I want to control my inverter pulses So invert pulses means nothing but switches will be there. Inverter is all about switches. Three-phase inverter will have 6 switches. I will have to control the on and off movement of my switches in such a way that I will get different voltage and different frequencies. So how to control that, how to write a PID controller, some code will be there. That's a different point. That's a different point of discussion. We will see that is not required as of now. But we know that by controlling these two, let's say this is voltage control, let's say this is frequency control. Using this kind of voltage control and frequency control, let's say we are giving pulses to my switches in the inverter in such a way that I will get a variable voltage, variable frequency as the output of my three-phase inverter. Now this three-phase AC source so is a balanced three-phase voltage source of variable voltage and variable frequency. Now I will write here, this is a balanced three-phase source of variable voltage, variable frequency. We call it as VV, VF source. Now this, if I will give this supply to my induction machine stator. Okay, anyhow, here we will have a rotor, and this is the stator of induction machine. Now here we are able to supply voltage and the frequency, which are variable. Now as soon as I have achieved this variation in the frequency, definitely my synchronous speed is not fixed anymore, right? This is the beauty of a power electronics system, where by introducing just a simple power electronic systems into the supply system, we are able to achieve variable voltage and variable frequency source, which is exactly we need for a precise speed control of a induction machine. Now as I achieved the variation in my frequency, it's not a matter. Now I can achieve a very good speed control, right? Now we will see what is the logic behind this one. So what are the what are the limitations of this? Now what are the conditions I need to follow to get a speed control, and how we can achieve a very good speed control using this method? Now suppose we have a induction machine. Okay, uh, let's see what happens whenever we change this frequency, whatever we need, whatever frequency we need to. Now, for example, let's say, let's take a small, okay, okay. Now let's say we have this kind of motor here. Now this motor have its a rated speed and also rated frequency. So let's say it's n rated and also frequency rated. We know from the basics of a machine the voltage equation, per phase voltage equations we know. We have discussed that V rated per phase is equals to 4.44 phi rated kW, that is window factor, which is the multiplication of kp/kd, pitch factor and distribution factor, multiplied by frequency, multiplied by the turns. Here not n is not speed, it's turns, you can say, or n dash, or okay, just write t. Let's not confuse it with the speed. Okay, now we have this kind of equation, basic voltage equation, per phase voltage equation for a motor. Now if we see the flux formula from it, phi rated is equals to V rated per phase divided by 4.44 kWt into F, right? Now once our machine design is finalized, I can't change the pitch factor because that is fixed. My distribution factor is fixed, and my turns are also fixed, and 4.4 is also a constant. Now this entire thing is a constant. I will separate it. K into V rated per phase divided by F rated. Now if you see here, my flux rated is proportional to V rated by F rated. Is proportional to the ratio of V and F. Suppose my rated voltage, let's say my rated voltage per phase is 400 volts, and my frequency of the machine is 50 hertz. That is the rated frequency, and my it's a 4-pole machine. Now, what is the rated speed of the machine? N rated will be 120 F by P, 120 into 50 by 4. How much it is? 1000 it's 120 F by P, right? Yeah. 1000 or 1500? It's 1500. Yeah, 1500 RPM. Now, these are all fixed now. If I want to run my machine at a 25 hertz frequency, since now I have my power electronic system, I have an inverter which can give a varied frequency. Therefore, now I want to run my machine at a half of the rated speed. Now, because if F2 is a 25 hertz now, what will be the N2? 120 into 25 by P. P is fixed, so it's 750 RPM. Now, since I have reduced the frequency, I will get the variation of speed below rated speed. So that's obvious, because frequency is directly proportional to the speed. If we keep on increasing the speed, you will get a above rated speeds. If we reduce the frequency, you will get a below rated speeds. Now we can see we are getting a speed of 750 RPM when I try to run my motor at half the rated frequency. Now, by keeping the voltage constant, here I have not changed the voltage. Now here voltage is still 400 volts. Okay, I have achieved the 750 RPM. Very nice. I have an inverter which will give different frequencies. I keep on reducing the frequency. I keep on getting different speeds. Now, can anyone tell me what is the problem with it? Can I just reduce the frequency, keep on reducing the frequency to achieve different speeds? Is there any, is there something wrong with this method, or is there something which we are missing? But everything is fine. I am getting a variable speed, variable frequency. I'm getting a speed control. What is wrong with this method? The biggest problem which we are overlooking here is I can't just keep on reducing the frequency, because if we keep voltage fixed and we keep on reducing the frequency for speed control, then the flux rated will just go up, and up. Now, from this formula, we have seen that flux is proportional to V by F. Flux rated is proportional to VR by FR. Now, at every case, we are keeping VR as constant, and we keep on reducing the frequency like this. Now, from 50, we came to 25, and again 10 hertz, 5 hertz. Now, my requirement of rated flux will rise up and up. So why is that a disadvantage? Why can't we have a more rated flux there? Again, there is a yes. Someone is saying something. Anil, you want to say something? Okay. Uh, we can't hear you. Maybe you can type it in the chat box. Okay. The problem with having this kind of high rated flux is my flux is actually depends on the magnetic intensity. We know that flux rated is proportional to B max. We have a formula also, 4 by P B max LR. Now, as we are increasing the rated flux, we are actually increasing our rated magnetic field intensity. That is units is Tesla or Weber per meter square. Now, As the rated flux increases, my magnetic rated B rated will also go up. Now my motor or any transformer or motor, they are designed based on some BH curve. So you might have heard about a BH curve, right? Now x-axis is H is proportional to MMF, right? Ampere turns. So it is proportional to magnetizing current. And here we have x-axis is B. Now it is proportional to flux, right? And let's say we have some kind of curve like this. Okay. Now here we have some knee point right here. We will have like this curve. It goes into like this. It's B rated. This curve is a current curve. We can say the x-axis. It's a in magnetic field intensity, that is H. Units are ampere turns, and the x-axis is the magnetic field density, that is B, Weber per meter square. Now let's say we are having B rated here at 5 rated. I have reduced my frequency half. 52 I went to 25 hertz, right? I have just reduced my frequency to half. My flux will go up two times of flux rated. If my flux goes two times, my rated density also goes two times. Now let's say this is one time, and it's just increased two folds. Now my new B rated is here, B rated new. Now what is the current for it? You don't know where the current is. Since for a small increment in the flux, you can see there is a large requirement of magnetizing current. You have to just keep on going to the curve where you will get that kind of B rated. So for this new magnetic field density, to achieve that rated flux, the amount of magnetizing current drawn by your machine will be very high. Now when you are drawing such kind of high current, it is very obvious that your machine will go into saturation. Now you can see this is at a above this knee point. You can say that your machine enters into saturation zone. Now to avoid this kind of situation, because if I just twice the flux density, my current drawn will be very large and my motor is going into saturation region. Now how this can be avoided? How can I avoid this problem? Can anyone have any idea? It's a very simple logic. I will have to reduce my frequency to have a reduced speed control, but at the same time, I don't want to increase my flux. I don't want to increase my rated flux requirement. So, how can I keep? So, formula is simple. The relation is simple. Flux rated proportional to V rated by F rated. I want to reduce frequency, but I don't want to increase the flux. How can I do it? So there comes the voltage factor in the numerator. Now, as I reduce my frequency, if I reduce my voltage also along with the frequency such that I will maintain the flux constant. Let's say it's 400 previously, it's 50 now. Now I want to get a speed control below rated speed, so that's why I reduced my frequency to 25. I will also reduce my voltage to 200, just half of it. Now here also my flux ratio is 8. Here also my flux ratio is 8. So in both cases, even though I am reducing my frequency, my flux rated requirement is still the same. My motor won't draw large magnetizing current. My motor won't go into saturation region. So that's how by keeping the flux level same, we can achieve speed control below the rated speeds. That's how, because now we have a variable. How can we reduce the voltage here? That's also possible because we talked about the supply we have. It's variable voltage and variable frequency. Now we can get a varied values of both voltage and frequency here. So yeah, now everything is fine. Now we will just see how do my torque speed curves look like in this condition. So where I am able to achieve different speeds, different frequencies, and different supply voltages. How would my torque speed curve looks? So that's the question. Now we know some approximate equations which we derived 2 weeks back for the torque and also torque equations, some current equations we have approximately derived by neglecting the rotor stator impedances and all. If you remember that, we have solved many numericals also. So if you remember the torque formula, torque is equals to some constant multiplied by S alpha by S square plus alpha square. You all remember this equation, right? We have solved many problems on this, where this equation K is equals to 3V1 square divided by 2 pi ns x2 dash, something like that. We will have that. Yeah. So this is uh, approximate torque equation where we have neglected the stator impedances or something like that. So yeah, we are just using this equation to just to have an estimate about our torque speed characteristics will look like how will my torque speed characteristic look like. Now if we take the te max, expression remains same, but instead of 3v1 square by 2 we will have 3v1 square by 4 pi ns x2 dash. So it's just k by 2 constant we'll have in case of maximum torque. Now using these torque relations, simple relations, we will see how when variable voltage is varied and frequency is varied, how my torque speed will vary. Okay. Now in the denominator of this constant k, we can see two terms, ns and x2, which are frequency dependent, because ns is equals to 2f by p, and x2 dash also frequency dependent. How? x2 dash is nothing but the reactance, which is omega l, and omega is nothing but 2 pi f. Now ns and x2 dash both are frequency dependent. Now if I just substitute that, now k is equals to 3v1 square divided by 2 pi 2f by p, and omega, sorry, 2 pi f into l. Now we can see that my torque equation is proportional to, there is a v1 square term in the numerator and f square term in the denominator. Apart from that, everything is constant. v1 by f whole square. Now this is a very important relation where our torque depends on the input supply voltage as well as the supply frequency. Now we already know we are keeping v by f constant, right? If we keep v by f constant, we can ensure that flux level requirement will be constant. Now keeping v by f constant, I am reducing my frequency to get a speed control below rated speeds. So this is straightforward. Now since my v by f is constant, you can see torque proportional to v by f square, my torque will also should remain same, because maximum torque is v1 by f whole square. Now this maximum torque, if you can see, my maximum torque won't change even though I am changing frequencies for getting a speed control. So now we can see, we can estimate how a typical torque speed curve would look like whenever I am having this kind of speed control. Now let's say initially this is a speed axis, it's a torque axis, and Okay, this is maximum torque, and this is the slip at which my maximum torque, because that's not a point of discussion right now. But the point of discussion is speed control. At this point, we have a rated speed. Okay, now my condition A would be supply voltage is V, and my supply frequency is F. I will have NS rated. Now I have reduced my supply frequency to half. I went from 50 Hz to 25 Hz. But to keep the V by F ratio constant, I will also make my supply voltage half, right? Now I have made my supply voltage is also half. So with this variation F by 2, I will get the new speed as NS by 2, right? NS is nothing but 120 F by P or 2 F by P. So my frequency goes half, my NS goes half. So this is NS somewhere around here, just half. NS rated by 2. So this point, I will get, my motor will have a new synchronous speed where the slip is 0. So this is my new synchronous speed of the motor. And now with this is my new torque speed curve of a motor where I have achieved a speed control. So now between NS by 2 to NS, we can achieve different speed controls by varying the frequency between F and F by 2, right? The point which you have to observe is, since the V by F ratio is constant, my torque maximum point remains same for the both cases. So for this case, it is V rated, comma F rated, but for this case, it is V rated by 2, comma F rated by 2, but the maximum torque remains same. So for various frequencies, if we want different frequencies like NS1, NS2, NS3, so on, you have to just vary different frequencies. Okay, this is ideal case. Why I am saying ideal, because not exactly ideal, but here we have neglected all the stator impedances, stator resistances, and magnetizing branch. Everything we have neglected. That's why there is no drop in those resistances. If we consider the drops as well, the actual curve may look like this. The only change will be maximum torque will not be exactly same because of the drop. It will just reduce a bit. That's it. So this is the speed, and okay, this is my T max 1, because the next time it will just change. Okay, now for the different value of frequency, now I will just this maximum speed may not be at this level, maybe at this, maybe it reduced at this level. Okay, maybe not that much. Yeah, maybe if you keep on reducing the frequency, it will come down like this. Okay, now you will have this kind of peak. You will maximum the maximum torque point which we can see keep on reducing, but still we are getting a precise speed control. Now for the same low torque, you are able to achieve different NS rateds. Now all these are points rated, but for different low torques you can able to achieve different speeds you are able to achieve. This is NS1, NS2, NS3, but this is the actual circuit where you are not neglecting any impedances. So maybe your maximum torque may not be same, but just a bit reduction in the maximum torque you can observe. But still all these curves are supplying my low torque even at lower and lower RPMs. So that's how you can achieve speed control using this. Now, okay, well, 1 second. So the system is fine. I have reduced my frequency below supply frequency to get a speed control below the rated speeds. From here to here, from this point, I have frequency rated, and from here to here, I have achieved speed control below rated speeds. Now the question is, can I run my induction machine at higher speeds, that is higher than its rated speeds? Let's say my rated speed at 50 Hz frequency is say 1500 RPM as we saw for a 4-pole machine. Can I run my induction machine at 2000 RPM? So it's just a simple logic, right? The answer is yes, of course we can. As we keep on reducing the frequency from 50, we came down to 30, 25, 20, so on. Now just increase the frequency, go from 50 to 50, 55, 60, 65. You increase it, you can get a speed control above rated speeds, right? So similarly in DC motor, we use the armature voltage control for the speed control below rated speeds, and field current control for the speed control above rated speeds. Similarly for induction machine, I can increase the frequencies uh, to get a speed control above the rated speeds. Now, an important point which we want to discuss for speed control above rated speeds is, okay, let's say uh, f I am increasing to get a speed control above rated speeds, but we know that flux is proportional to v by f. Let's say we are trying to keep our v by f ratio constant to maintain the same flux level. As flux frequency increased, I have to increase my voltage, right? This is the flux rated, this is the rated voltage, this is the rated frequency. Now I will increase my rated frequency. Proportionately, I have to increase my rated voltage to, to maintain the same flux level. Now there is a problem here. So can anyone see the problem? So the problem is, can I increase my voltage beyond rated voltage? Previously it's just reduction of voltage, okay, I have reduced, everything was fine. Now can I increase my rated voltage beyond the rated voltage? That's the question. So we should not go beyond the rated voltage than the specified rated voltage on the nameplate details. If my motor is a 400 volts rated motor, never go beyond 400 volts, because my motor windings are designed for that particular winding only, for that particular voltage. Now if you are going beyond the rated voltage, for which the insulation might not be compatible. So insulation is provided for rated ratings. Now if you are going applying more and more rated voltage, you are going beyond the rated voltage, your insulation might burn. It's not so the voltage increment beyond the rated voltage is not possible, just because we have the provision. So just because you have the provision to go beyond rated, it is not allowed to go beyond rated, because my insulation might burn. So for speed controls above rated speeds, my main point here is the point which I want to establish here, for very important point: speed control above rated speed, no need to maintain V by F constant. Why did we start with maintaining V by F constant? Because flux is proportional to V by F. If we reduce frequency alone, there is a chance my flux might go up such that my machine will draw more magnetizing current. Subsequently, my machine will move into saturation. That's why we made voltage also reduced so that flux will be constant. Now, same relation, I will increase the frequency for the rated frequency above rated speeds control. My flux will go down. There is no problem if my rated flux goes down. It's just that my rated flux level will be less. So my magnetizing field setup in the motor will be less. Might be it's not efficient. Might not my motor might not have sufficient flux density, but there is no reason to maintain V by F constant, because if you have to maintain V by F constant, you have to increase voltage also, which is not at all acceptable. So in speed control above rated speeds, there is no rule to we should not, there is no rule not like that. We will not maintain V by F constant. So only my flux will increase, but not rated voltage for speeds above rated speeds. Now for speeds above rated speeds, frequency will increase, my voltage will be constant, right? Now we have seen how my torque speed will look like for below rated speeds. Now how will my torque speed look like for speed control above rated speeds? Again, simple formula. The torque is proportional to V1 by F whole square. So that's what we got from here, this maximum torque. Now V1 is constant. So my maximum torque will vary with the square of the frequency. Now if I just increase a bit frequency, my torque will go down square times of that. So by a small change in frequency also, we will get a drastic reduction in the torque speed, like maximum torque. So that's understandable from this relation. So as my frequency increases, my speed will go up, that is direct relation to F by P, but my maximum torque will go down square times. Drastically, you can see that. So with that relation, if we want to draw my speed torque curve, speed in x-axis, torque in y-axis, and let's say my torque speed curve is like this, and this is my maximum torque initially. Now this is for rated voltage, rated frequency. Now, second. So now I have increased my frequency. If I increase my frequency, my speed will increase. Okay, let's say I am getting somewhere around this speed. Initially it is ns1. Now ns2 somewhere my speed is increased, but my maximum torque will go down. Let's say it came down to something around like this. I don't know, maybe drastic decrement. You can see that like this, and we further uh, and if we further increase the frequency, like this, you will get ns3, ns4 speed. Now if you see the maximum torque points, very drastically it will reduce like this. So at every instant you will have different torque max dash 2, or maybe torque max 3, torque max 4. So the decrement in the Tmax is drastic, and you can get here it is rated speeds, and from this point you will get a speed control above rated speeds. Now here, what you are controlling, flux. This is also a kind of flux control. So the interesting thing which we have to notice is it's very beautiful that in DC machine also, for the speed control above rated speeds, we call it as a field flux control. uh, in the induction machine case as well, for the below rated speeds, in this condition below rated speeds, what is my flux? It's constant because V by F is constant. But in this condition, the speed control above rated speeds, my flux is not constant because I'm increasing the flux frequency. My flux is going down. It's indirectly a flux control only. So even for induction machine, my speed control above rated speed, you can also call it as flux control. Likewise in the DC machine, that's the beauty. Every relation, every concept will come down, and they will all make sense now. They will make more sense. So yeah, that's how your combined uh, uh, diagram would look like. So yeah, if you combine this diagram with this diagram, so this is the rated curve, and below this you will have a below rated speed curves, and above this you will have a above rated speed curves. So this is how you will get a speed control in induction machines, and that which can be achieved smoothly and also precisely by power electronic systems. So with the advent of this advanced power electronic systems like inverter, the rectifier, and all, it's very interesting. Even for many applications like electric vehicle applications, and that's the future in the research areas. You can see for electrical engineers, the PhD. If you want to go for higher studies, masters or PhDs, the opportunities in the power electronics are vast, right? Starting from the kind of switches you use in the power electronics, like MOSFETs, IGBTs. There is a large area of research if you want to go to PhDs. And after you complete PhDs, if you want to do some kind of research or in some kind of research labs, power electronics, the areas in which people work in power electronics are numerous. So I would recommend everyone to go for higher studies and also explore the opportunities in the power electronics field. So it's really advanced field. You will simply amazed with the kind of advancement in the power electronics. So if you might also be having the power electronics subject coming semesters. So that's very important subject, and you have to you have to pay much attention in that concept, because this is where undergraduate level is where we start learning the power electronic concepts. So the stronger your basics are in the power electronics, the better you will understand the things in electrical engineering. It's very nice topic for the power electronics for electrical engineering students. So anyway, coming back to our discussion, so another interesting point which we have to look into here is, now we discussed many starting methods of induction machines last week. That is, exclude DOL. DOL is not any starting method. It's for just a small motors which have less inertia. Apart from DOL, we discussed reactor starting, auto transformer starting, and star delta starting. Now, why did we discuss this starting methods at all? Because initially my motor is drawing large inrush currents whenever I am applying rated voltage at the starting condition. So that's why I found some way where I can reduce my rated voltage at the point of starting. That's how we introduce some reactor in series between supply and the machine, or some auto transformer in series between supply and machine, or some changing my delta connected winding into star such that my voltage applied will be less. Now, all those problems will be solved. And how? Because we have a very good power electronic system here, which can able to give different varied voltages and different varied frequencies. Now, I will just simply start my inverter at a lower rated voltage, and I will then apply that rated voltage, lesser rated voltage to my machine. Slowly, once my machine picks up my speed, and I will increase my voltage and frequency very slowly with precise control, such that my V by F is also constant and also my machine is never saturated. So there is no requirement of any starting method now. Now I don't require any starting technique, and also I can also get constant V by F control of speed, and also my machine won't go into saturation, and everything is fine now by just using this power electronic system. I bypass the starting methods. I don't have to go for any starting method. Along with it, I am also getting a precise speed control. So now there is no question of any large interest currents being flowed, since my induction motor starting issue is also being addressed by this VVVF, that is variable voltage variable frequency process. These days everywhere we are seeing this kind of power electronic system. So even in traction systems now, people are not talking about DC series motor. Slowly, people are replacing this DC series motor with a power electronics based induction machine control, where we can achieve very good speed control. So yeah, so one more disadvantage of the DC series motor is because, okay, in the olden days, like previously, just before some 10 years or something, people are using DC series motor more and more because induction machine not capable of getting this kind of speed control. Now with power electronic systems, we are replacing, and even though DC series motor is having some disadvantages, because of we are not having any option, we were using it. What is the disadvantage in DC series motor? What is the biggest disadvantage in the DC machines itself? The big disadvantage is they have commutators and brushes. So the brush loss is there, commutators loss is there, and they require frequent maintenance and wear and tear will be there. There are a lot of disadvantages with the DC machine. Now, if you just replace my DC machine with a very good power electronic system based induction machine, you all know that induction machine requires very least maintenance because of its rugged construction and good operation, low maintenance. It have many advantages compared to DC machine. So that's why nowadays people are replacing DC series motor in traction machines with the induction machines also. So yeah, I hope the concept of speed control in induction machine is clear to you all now. We discussed in detail how speed can be controlled in induction machine below and above rated speeds. So just key points you have to remember is below rated speed, you have to maintain V by F constant to keep the flux rated constant. So if you don't maintain V by F constant and you are achieving the speed control below rated speed, your flux will go up, your machine might go into saturation. So to avoid that, you maintain V by F constant. So for above rated speeds, no need to make V by F constant, because for above rated speeds, if you go beyond the rated voltage, your winding might burn because of insulation problem. So above rated speeds, you just control the flux, that is flux will go down, your frequency will go up, you can get a precise control of speeds over rated speeds. So yeah, these are the key points in it. Now, I think with this, we can stop the discussion on the speed control of induction machine. Now, let's quickly look at the problems which we want to solve. So we have 30 to 40 minutes left, and we will solve 5 to 6 numericals that will be important for you to uh, to help with the assignment questions. Now, I request everyone to take pen and paper with them, and also calculator, so we can start solving questions again. These questions again are dependent on the formulas which we have learned 2 weeks back, because different models come in induction machine, but the core concept remains same. If we just remember some standard formulas in induction machine, solving the questions are very easy. Even in gate level, induction machine problems will come very easy. So I would recommend everyone to get thorough in induction machine concepts so that we will make sure that we will score all questions that comes from induction machines in GATE exams. So yeah, let's start the questions today based on the concepts of starting torque, maximum torque, and full load torque, slips and questions. Very simple questions. We will see. So let's see the question. The first question is a three-phase wound rotor induction motor has following parameters. That is, rotor resistance is 0.05 ohms per phase and rotor reactance is zero point 0.5 ohms, J 0.5 ohms per phase. Now here we are asked to neglect the stator impedances, rotational losses, and also the no load current. Now what was asked in the question? We were asked what is the slip at which the maximum torque occurs. So yeah, it's just if you remember the curve, this is speed, or else we can see it's a slip, and it is the torque, and this is the torque speed curve, and this is the maximum torque, and this is the alpha. So we are asking just alpha. Very simple problem, because it was already said that stator impedances and all are neglected. We know the formula for alpha is equals to rotor resistance by rotor resistance by rotor reactance. Alpha is equals to R2 by X2. We have used this formula last week also, and we have derived this formula 2 weeks back. So alpha is equals to R2 dash by X2 dash. Now, what is the rotor resistance given? This is 0.05 divided by rotor reactance 0.5. So how much is this? It's just 10%, right? 0.1, that is 10%. Okay, very simple problem. Now the question number 2 is how much resistance per phase needs to be added to the rotor to get maximum torque at the starting itself. Wow. Okay. Now we have discussed this kind of question today also. I will just go back to the curve where we have discussed. Yeah. See, uh, this particular diagram, if you can see here, this is for R2. Now I am keep on adding R2 external resistors to the circuit. So every time I am adding, my starting torque is improving. See, this is starting torque at initial date, TST1. Now when I increase the resistance, this is my new starting torque. Now this is my third new starting torque. Now they are asking, when can I get a maximum torque at the starting point itself? Now they are asking for this kind of condition. So I will add this point. So this will be my curve. So my at the starting itself, the entire maximum torque will be available at the starting. So again, a simple logic here. At the maximum torque, we know alpha, and we also know if the maximum torque itself is the starting torque, what is the condition for slip here? S is equals to 1. Now with that information, we will just go into the question. See, now the condition is T maximum is equal to T starting. But at T starting, we know that S is equals to 1, right? But at T max, S is equals to alpha, right? Now from these two relations, we know that alpha is equals to 1. This is the curve, this is the torque, and this is the speed, and this is the alpha, which is equals to 1. Now alpha formula we know R2 by X2, but now R2 is not just rotor resistance. We have R2 new, which is having the combination of R2 plus some external resistance. So that's exactly the question also. What is the new resistance to be added? What is the extra resistance that needs to be added? Now, since alpha is equals to 1, 1 is equals to R2 new divided by X2. Now, R2 new is equals to X2, which is, how much is X2? In the question it was given reactance is J 0.5. It is 0.5. Now R2 new. R2 new is nothing but R2 old plus R2 external which we added is equals to 0.5. So the question is how much is the external resistance that needs to be added. So R2 external that needs to be added is equals to 0.5 minus 0.05, that is the old one. So the answer is 0.45 ohms per phase. So if we can able to add 0.45 ohms per phase in each phase, you can get maximum torque at the starting itself. It is again, if you understand the torque speed characteristics, it's very simple, straightforward problem. How to get starting torque at the maximum maximum torque at the starting itself? You just keep on increasing the resistances, and the place at which you can get the maximum torque at the starting, you can achieve that. At that instant, measure the resistance. You can know how much you have added. So to solve it in a problem, we know that at the starting slip is equals to 1, and we also know the formula for alpha, slip at which the maximum torque occurs. Relating those two, we are able to calculate the new resistance of the rotor circuit. So yeah, so the next question is, to get half of the maximum torque at the starting, minimum how much resistance per phase is to be added to the rotor. So again, a similar kind of problem, but here they are asking that I don't need maximum torque at the starting. I just need half of the maximum torque at the starting. So if my torque, let's say this is my initial curve. So let's say that this is my T max, and let's say this is T max by 2. They are saying that I want to get this torque at the starting. So this is how my new curve would look like, right? Now to get this kind of starting torque, what is the R2 new? Again, what is the relation which we can use here? Because I know from the uh, question, T starting is equals to T max by 2. That I know. Now, what kind of relation can help me in solving the question? Now, let's go back to our last week's relation, which we know. Torque, electromagnetic torque divided by maximum torque relation. If you remember, it's 2s alpha by s square by alpha square. Even today also we have written this. Now see, alpha is at the place where T max occur, and S is the place where that is a running slip. Whatever torque, whatever slip at the operating torque, this can be any torque. If it is starting torque, S is equals to 1. If it is a full load torque, S is full load slip, like that. Now this is the relation we know, and from this relation, we know that replace TE with starting torque. Now TST by TE max is equals to 2 times of, now S is equals to 1 now. The slip at which starting torque occurs is 1. So I am substituting S is equals to 1 here, 1 square plus alpha square, right? From here, we have to calculate the alpha first, then only we can get anything related to how much the main question is R2. So how can we calculate alpha from here? Now from the question itself, it was given that T starting is half of the T maximum. Now what will be the value of this ratio? T starting by T max is equals to nothing but 1 by 2. Now 1 by 2 is equals to 2 alpha by 1 plus alpha square. Now here if you solve for alpha now, you will get a quadratic equation. Alpha square minus 4 alpha plus 1 is equals to 0. Can anyone solve the question for me? How much is the alpha in it? 1 minus 4, 1. Sorry? Yeah, 0.26. Yeah. Now, anyhow, we will get two values for alpha, and one value is 3.732, and another value which I got is, like someone said, 2.2679. Obviously, slip can't be more than 1, so this is an impossible value. So we should take 0.2679. Now, this particular slip we have got 0.2679. Okay, now what we have to calculate? The new resistance. But we know alpha formula is nothing but alpha nu is equals to R2 nu divided by X2. Now 0.2679 is equals to R2 nu divided by how much is X2? X2 is 0.5. From this you can calculate R2 nu. 0.2679 into 0.5. It's 0.13395. 0.13395 ohms per phase. Okay, now we are asked to see how much needs to be added additionally. Now you have to subtract the original. R2 external is equals to 0.13395 minus R2 old. How much is R2 old? 0.05. Subtract this one. This is 0.08395 ohms per phase. So this is the answer. So, but in the question it was asked in milliohms, so you can just multiply it with 1000. That is 83.95 milliohms per phase. This is the value of the resistance you need to add to the rotor circuit, so that you will get half of the maximum torque at the starting itself. So yeah, let's see the another question with the same data. See, the addition of extra resistance as in question 3 will make starting current to be dash percentage of the original, that is without extra resistance. Okay, so yeah, we have two cases now. Case A, old circuit will have old resistance R2 old and starting current old. Now with the new circuit, we have added some additional resistance, that is 83 milliohms. So my R2 entire will be R2 old plus that 83 milliohms. So I have R2 new, I know the value also. Now starting torque will be changed, because we know starting torque is equals to voltage by impedance, that is root of R square plus X square. Now V anyhow is constant. Now it's inversely dependent on the impedance only. Now we will have a new starting torque. Okay. Now they are asking just addition of extra resistance will make, what is the percentage increment in that to this? Now see, this is very simple. It depends on the impedance. So the new starting torque, current divided by old starting current will be inversely proportional. Here it will be old impedance. That is, how much is the old impedance? It is new here. So new in the numerator. The denominator will be R2 new whole square plus X2 square. X2 is anyhow same in both cases. In the numerator, R2 old square plus X2 square. Now how much is R2 old? 0.05 square plus 0.5 square. How much is R2 new? In the last problem we have selected R2 new is 0.13395 square plus X2 is same. So someone can calculate it for me. I will also calculate and let's start with the answers. Okay. So I got the ratio as 0.9707. So it's nothing but IST new by IST old will give you 0.97 ratio means IST new is 97%, 97.07 percentage of IST old. So this is the uh, percentage of the starting new starting current of the old starting current. Yeah, that's a percentage. You just have to take the ratio. Okay. Okay, now we have another set of data for another question. So the question is for a three-phase induction motor with negligible stator impedances. Here also we have to neglect the stator impedances and rotational losses as well as no load current. The question is the maximum torque is equals to 3 times of full load torque, which is itself is equals to 2 times of starting torque. So it's all about ratios now. So if it's in the ratios, the problem is going to be very easy. You just have to write the ratios here. 3 times of full load torque, which is what 2 times of starting torque. So they can ask any kind of relation between maximum torque and starting torque, full load torque and starting torque, full load torque and maximum torque like that. Okay, let's see what the question is. The question is the maximum torque occurs at dash slip. So again, we are just asking the value of alpha. So what do we know about alpha? Alpha is equals to R2 by X2. But the problem is, in this question, this data of this equivalent circuit parameters are unknown. So how to solve for the alpha now? Can anyone can give me the idea? It's all about ratios now. Okay. So we know that the ratio between the torque and maximum torque we have written it here. So the ratio between T and T max is 2s alpha. So I will just write the relation again. 2s alpha divided by s square plus alpha square. Right? Now I can go for this ratio. I can write this Te as starting torque or I can write it as full load torque. If I write it as full load torque, I need to know the value of full load slip, which I don't know at this point. So at the starting point, but I know starting slip is equals to 1, so I can eliminate the value of S here. So I will just replace T by starting torque, maximum torque is equals to 2 alpha plus 1 plus alpha square. Now what is this ratio from this relation which is given in the question? What is the ratio of T starting by T max? It is again 1 by 2. So from the first T max is equals to 2 times of starting torque. So 1 by 2 is equals to 2 alpha by 1 plus alpha square. So again we are here with a quadratic equation. Alpha square minus 4 alpha plus 1 is equals to 0. So is it the same equation which we have here, alpha square minus 4 alpha plus 1? Yeah. So again, the slip at which the maximum torque occurs is 0.2679. So yeah, this is the slip which we can get the maximum torque at. So maximum torque can occur at this slip. So yeah, this is the last question for today. Let's see what they're asking in this question. Full load slip. See, yeah, for the first question, if we replace a TE with TFL, we need to know the value of full load slip as well as alpha. So we made this TE as starting torque so that I can eliminate S and calculate the alpha. Since I know the alpha now, I can use this alpha information to calculate the S here. So now I know the formula, electromagnetic torque by maximum torque is equals to 2S alpha by S square plus alpha square. Now, since I know the value of alpha now, I will replace the electromagnetic torque by full load torque, maximum torque, as full load alpha full load square plus alpha square, right? Now, yeah, we know the value of alpha, and also what is the ratio of full load torque by maximum torque from the relation. Full load torque by maximum torque is 1 by 3. 1 by 3 is equals to 2 SFL multiplied by alpha. How much is alpha? 0.2679. 0.2679 divided by SFL square plus 0.2679 square. Okay, now if we have to solve this equation again, we will have a equation, quadratic equation. SFL square minus 6s into 0.2679 plus 0.2679 whole square is equals to 0. Okay, so yeah. Now again, can someone solve this equation and let's see what happens. 1 minus 6 into 0.2679. C is 0.2679 square. Okay. 1.56. Now SFL I have got two values, 1.5614 and other value is 0.04596. Okay, obviously SL can't be greater than 1. This is not possible, and my full load slip is equals to 0.04596. If it is in percentage, it will be 4.596 percentage. Always you have to make sure what uh, ratio, like what are the units in the question. Here also maximum torque is at the dash percentage slip. So the percentage slip will be 26.79 percentage. Okay. Same way, please make sure what kind of units they are asking in the question. Here milliohms per phase, and that's the ohms per phase, and this is the percentage, 10 percentage. Okay. So yeah, this is the point where we will stop our discussion for today. And as a quick summary of of our today's discussion, we will just see what all we discussed today. And we started with the concept of speed control, because the basic things in a machine is starting a machine, speed control of a machine, and stopping the machine, which is the braking, electrical braking. So we discussed the starting last week, and we are discussing the speed control today. We are discussed. So with the basic discussion, what exactly is speed control, how can we achieve with earlier methods we discussed, how people used to do, and what are the disadvantages with that, if it is a resistance control or if it's a voltage control. And with the disadvantages, we have moved to the advanced system of power electronic system based speed control, and how we can achieve a variable voltage and variable frequency from a three-phase 50 hertz supply. Once we have this kind of variable voltage, variable frequency supply, how can we achieve a speed control below and above rated speeds we have see, and what are the basic conditions to follow to achieve such kind of speed control we have discussed. It's very straightforward and pretty not very difficult kind of subject here, and it's a very straightforward question problem. And now we have understood how we can achieve smooth and precise speed control below and above rated speeds. So with that, we have started solving some questions for the assignment purpose. So we have solved questions based on the equivalent circuit, and also ratios of starting torque, maximum torque, and also the full load torque. So yeah, with the simple relations and proportional relations, we have solved 6 problems. And I will suggest everyone to attend for the next session from 7 to 9, where some more problems based on this assignment will be discussed. 6 problems will be discussed along with some concepts. So yeah, that's all for today's discussion. And if you have any kind of questions, I would suggest everyone to come up and ask some questions, and we can discuss in the class itself. And if you don't have any questions for now, it's okay. You can also raise questions meanwhile in the discussion forum. We will get back to you as well. So, any questions on today's topic? Yeah, thank you, Govind. Yeah. Sorry, I have not seen some messages by Anil. Sorry, yeah. Yeah, by reducing voltage, so it will be constant. Yeah, yeah. Thanks, Govind, and thanks, Priya. Thanks, Mr. Nandakumar. Thanks, Daya. Okay, if you don't have any questions, again, thank you all for patiently sitting and listening to our discussion for 2 hours. And yeah, we will meet next week, same time, 4 to 6 p.m., and we will discuss more concepts on AC machines. So, looking forward to discussion again, a good discussion with you all next week. So, thank you for giving me this opportunity of discussing with you, and see you next week. Thank you.